The motivation for this talk was like I perceived a discrepancy in like the perception of like Blip-like synthesis, like band-limited synthesis, like I do it, and everybody else perceives how it's the overall how it's done, how I find code on the internet, and even people who are way smarter than me think, well, it's hard, it takes a lot of computation time or so. And I always go, no, it's just easy peasy, and it's such a useful thing. Maybe I'm doing something a little bit different than everybody else or so. I was given similar explanations to some of my students or so, and it turns out they were amazed at the usefulness of that, and they also said, well, but it's absolutely none of that is taught in any kind of textbook or so. So I thought, well, maybe I have some new stuff to show here or so that is a little bit useful for you. So yeah, so the talk will be in 3 parts. First, I will explain a little bit what Blip is about or so. It might be boring for people who already are in DSP or who do synthesizers. So has anybody of you done any blitz synthesis or blip or blap or whatever or so before? Yeah? Okay, that's quite a lot. Yeah. Okay. So you might know that it's useful for like creating like waveforms like Sawtooth and Square or PWM or even hard sync or so. Yeah. So yeah. Here I'm going to talk about different things, but let's first go through Blip. Yeah. So in continuous time, it's quite easy. When we have a pulse train with alternating pulses and we integrate that over time, we get a perfect rectangle wave. If we integrate the same pulses, minus some DC, over time, we get a what's it called? Sawtooth wave. Yeah? Easy peasy, everybody knows that. So unfortunately, we're not dealing with continuous time in digital signal processing. We're dealing with discrete time, where unfortunately the samples are not exactly on where we want them to have. So the pulses are kind of in between. What we do is we just move them to the nearest sample and we're all set. Okay. It's not the case. Yeah, it would be a strange thing. Yeah. So what we do instead, we look at these only, well, and we only look at the one sample here. So if you know the sampling theorem, you know that there is an exact mathematical formula to say what all the values of these samples should be to represent this one. So it's like a sync curve, yeah? You know that, I think, yeah? But the bad thing, so the good thing is we know exactly the values. The bad news is it extends towards plus and minus infinity in time. So what we usually do, so yeah, these are the discrete samples. What we do, we want it also locally in time. We have a window function. We apply the window function, and we have it locally in time. This, of course, will introduce some errors. As you know, we can minimize that by dilating that a little bit, so make the pulse a little bit wider. It's still a sync function, but widening it a bit. And we have several parameters, how we create sync waves. So what we usually do, we create a bunch of those, pre-calculate or so, with fractional delays. So this is kind of from one sample to the other with different, here's like 8 or so, I think, with different subsample delays. And as you can see, if I superimpose this time shifted, it's quite a smooth thing. So, but we only need this once, yeah. So we can just time shift it by one sample to get to the next integer sample value. So the good news is, for proper blitz synthesis, we need just a bunch of those pre-calculated blitz and put them in some area somewhere. And anytime we need to have an edge or a discontinuity, like in a square or a sawtooth wave, we just throw one of these into a tiny delay line. Yeah. Just throw all like 16, 8, or how many samples you have per blit into that, and you're set. The thing about this is you should, if you implement that, have a producer of those blitz that puts it into some delay line, and a consumer, which is an integrator. And it's usually a good idea to use a leaky integrator for that. So because if you do some modulation, or if you scale volume, or even if you use floating point, you will have some errors. And it smoothes out all those errors over time that you could make or so, and it doesn't build up DC. So if you make that, there's some ballpark value. So what you can select, the number of snippets or blips, or how you call them, well, should be like bigger than 64. 64 is the number of subsample blitz you pre-calculate. Then the length of these blips, I think 8 is kind of the practical minimum, or so kind of works, but well, we should perhaps make it a bit longer. The dilation is how you stretch it or so. If you stretch it more, you will get less high frequency content. But if you don't stretch it at all, you will get a little bit errors in the high frequency range. Yeah? It's not so very bad, this error, because you know, this is usually followed by an integrator, which is also a kind of a low-pass filter. So it's, in this case, this works in your favor by low-pass filtering the error that's on the top band, which most of us don't hear anyway. Yeah, then there's the window function that you apply to get the limited time. And this window function is actually quite important because we have an integrator coming after that. We must make sure that all of these snippets have exactly the same DC value. Or if you sum up all of these, they should the sum should always be the same. So I arrived at a function that's similar to that. It's kind of like somewhere in between Hamming and Henning window or so. And well, I didn't really ask why it's like this. Just trust me when I say, well, this is kind of a window I use, and it gives the best, almost ideal DC response for all these snippets there. Then you have to ask, well, do I do interpolation if I do it practically? So you could do a linear interpolation in between those, but it depends. It depends if you want to do a, for example, a triangular wave. You get a triangular wave if you chain like 2 integrators, like an integrated square wave becomes a triangular wave. But this is even more sensitive to like slight errors in DC, and slight errors in time or so will also show there. So if you do triangular waves, I suggest you do interpolate in between those. If you're only going for sawtooth or square waves or something like that, it's usually the best just to increase the number of snippets and you're all set. So these are just ballpark figures or so, yeah, for practical implementation. There's nothing very scientific about it. It's just what I figured out is the minimum what you should probably do if you want to do practical band-limited impulse train synthesis. So this is a tiny little bit of code. I think we won't have time to go deeper into that or so. I have a blip tab and the wavelength and the next edge. The nice thing about it is then most of the time if you do blips, you do nothing. You just wait for the next edge to happen. Then between that, there's absolutely nothing to do, apart from the integrator or so, which should not really count or so, because as we can see later, we can, if we work in a polyphonic or paraphonic mode, we can have only one integrator instead of integrators running in parallel or so. The other thing, I've seen it done wrong many times, is you should use a wavelength. A wavelength also that covers also the fractional sample time, and not do anything with a phase accumulator. If you use a phase accumulator for blip synthesis, you're doing it wrong. Or you're doing it not the way I think is right or so. And I just say it, well, because I saw it so often that people use a phase accumulator, and then step by step they use a division every sample or so, and it's just, okay, we can go deeper into this later or so, if we have time. Okay, this code is also not production quality or so. It's just for show. Yeah? This is also, so the basic thing is, this is like the producer of those blitz, puts it into a delay line, and this is like the integrator with a very crappy implementation of a delay line, as you can see here, with an unsigned Charison index, which overflows, which is defined behavior, by the way. Just if you use overflow on integer types, or also make sure that you use unsigned types. Because signed types might overflow as well, but it's undefined behavior. Okay, so the next part is an oscillator bank. So what we're trying to do is a fully polyphonic, that means 128 voices, or not even voices, say oscillators. That means 128 square waves. So that would mean 128 Blitz generators and 128 integrators. Well, we can optimize that, or can we? So what we can do, I have no proper illustration, but you can easily imagine that. It's easy if we have the producers of Blitz, we can just have one integrator at the end instead of 128 integrators. Just if we put everything into one delay line. Understand that? I think, yeah, it's easy peasy. So, but instead of 128 Blitz generators, we only use 12 Blitz generators. Number 12 is easy because it's for every semitone. And we're going to make every Blitz generator similar to a octave divider, like it's found like on older analog machines or so. So, as you can see, I have here like 3 octaves. In reality, it's going to be quite more octaves, like 10 or 11 or so. Well, you see here, well, by the way, this is now that we know how to do blips, this is supposed to be a blip, yeah? Not a single sample or so. So we have now the blips that form a square wave at the top octave, 1 octave below, and another octave below. And if we combine that, these blips, we have like, well, as many blips as the top octave, well, 1 less if you count, if you subtract the 0. And if we integrate that, well, we get the sum of like all those. And we save some computation by combining these that are occurring at the same time. We just, before we throw the blip into our buffer, we calculate what is the sum of all these at a given time, and we save. We are actually getting like 10 or 11 octaves with only one oscillator running at a quite high frequency. Yeah, this is a kind of the pattern or so, as an example or so. So the changes for the top octave, you see, well, it changes every time. For the octave below, every second time or so. So this is the pattern where you have to sum the actual scales of the oscillators, because we will have scales for the different octaves later. It might not be obvious, no, but well. So here I have, like, imagine these 12 oscillator banks. So we have some with 10 octaves, some with 11 octaves. And this is equivalent to a representation I write here, where I have it like in a linear fashion. It extends a little bit upward, but I found it a little bit awkward to show it all here. So yeah, so this is now our oscillator bank, as you can imagine. So we have 128 oscillators with only like 12 producers, which work by kind of octave dividing. Sounds like that. Yeah, it was not all 128, so you won't hear the lowest notes or so. Yeah, so yeah, cool 128 square oscillators. Now the question is, what can you do with it? You can actually use this oscillator bank in a similar fashion as you use oscillators in a drawbar organ, like well, the typical Hammond organ or so, where you set mixes for those. And well, here, like each box signifies a kind of a switch. Yeah? So we'll have here mixes where we mix the square waves as if they were harmonics. And actually, I don't know if you can see that here, you can get a perfect sawtooth wave by mixing square waves. So it's only 4 octaves of square waves shown here, and you see it's a little bit steppy. But if you add more, the steppiness gets away, and you kind of get a perfect sawtooth wave. It's already done in kind of old analog synthesizers, like the Poly 800, that had only 4, and it was a kind of convincing sawtooth wave, although not perfect, but well, good enough. So now the question is, where should the keyboard go? We only have one axis for that one. So now, so I think it should go here, the keyboard. Yeah, so let's see. Yeah, it must go here, sorry. It looks awkward, but trust me, I know what I'm doing here. So if you press a key or so, you set all the switches along this line. What does it mean? That must mean, okay, so these are all the Bs now. So, by the way, these are binary switches, yeah? And just like you set the contacts in a Hammond organ or so, you have these, you set these switches, and now these oscillator can be it's the fundamental of this. It could also be like the first harmonic of the octave below, and so on. Yeah? So these single oscillators serve the same purpose as the tone wheels in a drawbar organ. Yeah? So the level of a single oscillator, of a single source, is like the sum of these switches times the mixing values here. So here's the mixing value for the sawtooth wave. You see, if you add them at this, like with always having volumes. And the nice thing is, if you simply shift that, you get a sawtooth wave, but with 1 octave higher. And you can do that in real time. So that was the output of this oscillator bank. But with this mix shifted, slightly interpolated, of course. Yeah? And you can still do it fully polyphonic. So what you have here is like 128 oscillators times 8, you have like 1024 switches. But there's an easy way to calculate the actual scale for each oscillator. If you use these switches as actually bits of an integer or so. We can go to that later if we have time for some questions or so. This top divider thing was also used in the Korg Lambda. This is actually where I got the idea from. It's also in this product I made, where it's the basis for a string machine. And, oh, we sell boatloads of these things already, but this is not about this thing. So that was the oscillator bank thing. We're running out of time, so I must hurry up. So the other thing is sample rate conversion. You know how that usually works? We have the input sample rate here lower, and we have the target sample rate, and we have some windowed sync filter where we sum that and arrive at one output sample. What if we do it the other way around? We have this sample here, and we just have some windowed sync, still some windowed sync, but we calculate the contribution of this sample to every output sample. Is that possible? It is possible, but it's not a very good idea to do practical sample rate conversion, but I'm doing it anyway. Yeah. So what if the filter is actually very slow, very small? So you say, well, that cannot work. It produces aliasing. Right, this produces aliasing. That's exactly what I want to do. So what I also do is like differentiate the input signal and integrate the output signal at the end. Trust me, I know where I'm going with that. Yeah. So what we do here is no more a filter, but it's kind of a blip, because you just drop a blip with a fractional time, and in the end, you integrate it. So you can use blips for sample rate conversions with proper aliasing. So I have an example for this. Does anyone of you recognize this font? Exactly, yeah. So this is the Atari speech synthesizer.
Atari 1040 ST computer speaking here. Can you hear me?
So this is like a port of the Atari ST speech synthesizer, as I did this like 7 years ago, and I released it or so, but people were kind of unhappy. They said, well, it doesn't just sound right. Although I said, well, I made everything sound right. I even increased the sample rate or so, yeah. Until I figured out, well, the output stage, the converter was running at like 8 kilohertz, and there was really no proper oversampling. So the DAC had horrible aliasing, but it was part of the sound.
Atari 1040 ST computer speaking here. Can you hear me?
So there's a lot of aliasing, but this introduces some new kind of like new formants or so, which are very characteristic of the sound. And if you want to model this, well, here we go again, you have to do this. So this is what it looks in time domain. This is like kind of the perfect thing, but, well, it sounds boring as hell. And this is kind of the output using the blip for sample rate conversion. It's not sample and hold. You can see that it's not just DC plateaus, but the exact time where the transition happens is exactly at like a little bit below 8 kilohertz or so. And you can, if you implement it, you can even modulate that in real time, get some very nice effects. This is, can you see that? How it looks in frequency domain. You see here, this is kind of the formant of the speech, synthetic formants, which make the speech, well, more or less intelligible. Anybody knows what formants are? Okay. Yeah. This is the same, done wrong, but wrong in a way that it sounds well, right, like it sounded like 30 years ago. And you see all this aliasing, but the aliasing is not at all correlated to the output sample rate. No, it's correlated to the input sample rate. And done very easily with Blit. Blit at the input sample rate. So that was kind of it. Brief demonstration of Blit, what you can do with Blit. Some hints, because I've seen it being done wrong so often. Use a wavelength, don't use any phase accumulator. Use an unsigned in for wavetable length and not a float or something like that, because, well, if you use it as an index, you won't sometimes convert it to an integer anyway. The other thing is process in blocks, not in samples. So this will perhaps increase your latency a little bit in the order of like 16 samples. But, well, since I've had a talk where Google is trying to get the latency down to 10 milliseconds, which is like in the order of hundreds of samples, we should see latency in the order of like 16, 8, or whatever samples, a little bit more relaxed and do block processing. Because then we only need to check once per block if we have to set a new edge, and not once per sample, which gives us even more power to do nothing. Exactly the time from one edge to the other, it's important to do nothing, and that's the best we can do DSP-wise, because that way we get the best performance, of course. Another thing to note about this, because we're operating in time, and not with a phase or so, and the wavelength actually determines the workload, this kind of signal processing, if you leave away the integrator, is kind of independent of the sample rate. We might even come to the perverse situation where increasing the sample rate might save you power because you have more relaxed, you can work with smaller blips or so. So, yeah. So that's pretty much everything. I think it's 25 minutes are over. If you have any more questions or so, or want to look at some code or so, yeah, feel free to ask. Thank you very much.
Thank you, Stefan. Do we have any questions? We have time for one question, so feel free to ask.
Oh.
No, thank you very much for a great presentation, Stefan.
Yeah, okay, thank you.